estimation, high-dimensional data analysis, statistical machine learning, and etc. And he has won many prestigious awards, including COP's President Award in 2008 and IMS Medallion Lecturer in 2009, and among many others. And Professor Tony Kai is going to talk about federated learning for nonparametric function estimation, framework, and optimality. Thank you, Professor Kai, and look forward to your talk.
Thank you. Yeah, it's very nice to be here. And I want to talk about some recent work on federated learning. And recently, I want to begin with some general discussion. Recently, there's a lot of discussion about the relationship among different areas with a lot of overlaps between, I would say, different fields in statistics, data science, machine learning, and AI. And there's no clear boundary between any two of them. But you will see there are some distinctions, say, between statistics and data science and so on. And we certainly have heard about the big data and the AI almost every day in news and general literature. According to Tom Sargent, AI is actually statistics. It's not just statistics plays an important role in AI. According to him, AI is simply statistics. And all AI uses statistics to solve problems. Certainly, he's a good friend to all of us. Maybe some CS people don't agree, but at least it shows that statistics is very important in the age of AI. And if you think about statistics, it's very different from hard science like physics. Our field is driven by applications. And there are lots and lots of applications in many different areas. And we develop methods for those applications. And some we know why they work. And some we actually don't know why they work. And deep learning is one such example. So in terms of theory, actually, we know relatively little compared to either the range of applications or the collection of methods. So it's paramount to theoretical statisticians to understand certain methods or certain problems in some more principled way, not just proposing a method. And one such area is federated learning. If we think about the general framework in classical statistics, since I would say 1940s, so for the last 80 years or so, we have tried very hard to develop theoretical framework for statistics. So in the conventional framework, the goal is to develop optimal procedures, whether it's for estimation or for confidence interval or testing. Any statistical problems, we want to know what's optimal, what's the best way to do things. And this is with respect to sample sizes and statistical model. And under this framework, we have studied a lot of properties, for example, admissibility, efficiency, minimixity, adaptivity, and so on. And statisticians have spent a tremendous amount of effort on each of these topics. And if today I'm going to use minimixity as an example for this discussion. So if we think about classical minimixity, and we observe some data, and whatever we observe and how much we observe, we call it X. And this X comes from some distribution. And this distribution belongs to some collections of distributions that we don't know. and we wish to estimate some aspect of this distribution. It could be the mean of the distribution, it could be the density function of the distribution, or it could be, say, regression coefficients. Anything that we want to know is a parameter of the distribution. And our goal is to first find such an estimate. We construct an estimate called theta hat. And then we want to evaluate the performance of this theta hat. And the minimax framework, we evaluate the risk by its maximum, the performance by the maximum risk over the whole parameter space, say, script P. An analogy of this is like we want to measure the accuracy of, say, a watch or a clock. How do we measure the accuracy of the clock? Imagine if we are able to compare the real time, the actual time, with the watch time over, say, a cycle of 24 hours. What's the maximum deviation? And that's the measure of the accuracy of the watch. And we certainly want to find the best possible watch, or try to construct the best possible estimate under this framework. So we want to find an estimate that minimizes the maximum risk. If we're able to do that, then we have a minimax estimate. And in this framework, that will be the best possible estimate, or in the analogy of watch, that's the best possible watch. So maximum deviation from the actual time is minimized. And that's classical minimaxity. I would say in the age of big data and AI, now we have something called post-classical minimaxity. And as a statistician, we still observe some data. We still want to analyze a data set called X. It comes from some distribution we don't know. And we want to estimate some aspect of the distribution called theta. It's a parameter. Again, it could be the mean, variance, regression coefficient, anything that we don't know. But what's different is that in this age of big data and AI, for a range of problems, we are no longer interested in any estimates. We are interested in a subset of estimates. So again, let's take the watch as an analogy. Suppose you have a watch and I have a watch, and you have a very expensive gold watch, and I have a junky electronic watch, very inexpensive. You don't want to compare your expensive watch with mine. Maybe my watch is more accurate. You only want to compare your watch with another gold watch. So in this setting, you're only interested in a subset of possible constructions of estimates. You're not interested in any, say, without constraint, any watch. So in this context, the first thing is try to construct an estimate that satisfies the constraint. So this estimate, say, let's call theta hat, and belongs to this set A naught. And we still measure the accuracy in the same way. We measure the accuracy by the maximum error. And within this constraint, we want to find the best possible estimate. So now the infimum is over a subset of procedures. And so in the context of watch, it means we just want to find the best possible gold watch. Say, Apple Watch, no matter how accurate it is, it's not good enough for me. So I'm only interested in a subset of procedures in the context of statistical estimation. So what's different from before? In statistics, in this framework, actually it's not completely new. In classical statistics, actually we have studied problems like this. For example, we want to find the best possible linear estimate. What's new is that constraint itself is often non-statistical. It's not something that we normally consider in classical statistics. So someone might wonder what kind of non-statistical constraints that's of interest to people. and lots of them. And the first one is privacy. And in the age of big data, actually, it's very easy to identify people from statistical output. And the question is, how can we do statistical analysis while guaranteeing privacy? So in this case, again, we are no longer interested in any statistical output or estimate. We want to estimate that guarantees privacy. And also, there are more and more problems that data is distributed. If you work with any high-tech companies, Google, Facebook, Tencent, or Baidu, the data is simply large, too big. There's no way you can put all the data under one roof or under one machine. They are necessarily distributed in different servers, maybe in different locations in the world. And there are other problems, for example, in medical data. If you want to study, say, diabetes, the patients, their record is kept at different locations. Like this hospital has diabetes patients, and that health organization has another set of patients. And there's no way you can ask them, say, can you give me a copy of your data? And I take back to my office and combine with all other data I get. And you're lucky if they allow you to analyze their data. And also, computation. In statistics, we care about the speed of estimates, how fast we can implement the statistical procedure. But to us, at least in classical statistics, it's often secondary. We don't really take computational speed as high as, say, statistical estimation accuracy. And one such example is MLE. If you take first class in, say, graduate statistics class, and we learn asymptotic properties of MLE. Under a set of conditions, MLE is optimal. Only later, you realize that that estimate actually is not possible to compute because the objective function is non-convex and other considerations. And then we try to approximate. And without knowing actually whether the estimate we compute at the end after a few steps of approximation is exactly the same as the one we proved in the theorem. And now there are more and more problems. Actually, there are fundamental tensions between computational cost and the statistical accuracy. For a range of problems, anything that can be computed fast is not statistically accurate. Anything that's good cannot be computed fast. And also in machine learning, there are a lot of discussion about fairness of a machine learning algorithm. In all these problems, you can see that we are no longer interested in any estimates. We are only interested in certain estimates with certain properties. So in this framework, where you want to study the problem or understand the interplay between statistical accuracy and something that's non-statistical, whether it's privacy, communication cost, computational cost, and so on. So roughly speaking, we want to understand something statistical with something non-statistical. And federated learning is one such example. It has been very popular in the last few years. And it can be illustrated by this picture. Suppose we want to study certain disease, say diabetes. And patients belong to different health organizations. It could be, say, you have some data from a community hospital. You have a way to analyze the data locally. But you must guarantee the privacy of your output. Otherwise, the hospital would not allow you to analyze that data. So you can output, after analyzing the data locally, you can output a privacy-preserving output to the central server. So think about you as a data analyst. You can go to the hospital, access their data locally, but you cannot take the original data back to your office. You can analyze the data and take away an output that preserves privacy. You can do the same for the next hospital, or in this case, medical center, and so on. So you can analyze the data locally, and you can take away an output that guarantees privacy. And at the end, you have a global model, and you want to aggregate all those privacy guaranteeing outputs, get a final estimate, or make a final decision. And this has been very popular, as I mentioned. You can see the number of publications. The growth is almost exponential. And you can see the number of publications in federated learning. It's very fast. So it has drawn a lot of recent interest in statistics and also in machine learning. So statistically, roughly, we can formulate the problem as follows. So we have one data set, and we can assume that data set, say, patients in one hospital. The data is IID from some distribution, and it's parameterized by theta and something else called omega 1. And the reason I split the parameter in two sets is that for the next data set, the distribution may or may not be the same as the first one. But there are something in common, theta, and so on. And the next set, omega 2, is different from omega 1. So under this framework, people want to study the problem collaboratively and optimally. So after analyzing the data, you can output something called transcript, a statistic called T1, and guarantees, say, privacy. And you can analyze this set of data and output something called T2, and so on. So after collecting all those transcripts in the central server, you want to construct a final estimate, and this final estimate is a function of T1, T2 to Tm. It's also a function of the original data, but it's not an arbitrary function of the original data. So the question is, how should we analyze individual data sets and output those transcripts such that the final estimate is optimal? And in terms of communication scheme, this is called independent protocol. Once you output a transcript, you don't send any message back. In more complicated scheme, it turns out that you can, because the central server has access to all T1, T2, all to Tm. So after putting them together, actually the central server has more information. It's possible that you can send a message back, and the data analyst here can reanalyze the data set and then send, say, T1 prime. And for simple problems, interaction or feedback is not necessary. And we don't consider feedback in this talk. But for a more complicated problem, it turns out feedback is strictly better than without feedback. And those quantities, T1 to Tm, is called transcript. And in terms of constraints, it could be communication constraints. If you want to do online learning, you want to do, say, instantaneous decision making. For example, shopping. If you get on, say, Google or Taobao or some shopping site, you often receive feedback recommendations right away. So in this setting, speed is everything. You cannot, say, wait for 10 seconds or even, say, 1 hour to analyze the data in the best possible way. You want to do it very quickly. But in medical applications, often the more realistic constraint is privacy. Constraint is needed because if we don't have any constraint, then the best possible way to do it is simply send the original data to the center. But as I said, that's often impossible. So under privacy, the problem can be illustrated by this plot. So we have data sets Z1, Z2, all the way to Zm. And after analyzing each data set, we output a transcript that guarantees privacy, epsilon delta privacy. And I will explain this in a moment. And after receiving all those transcripts, we construct an estimate theta hat. And there is something naive that can be done relatively easily, assuming we know how to analyze one single data set. Suppose we know how to handle one single data set. Then we can certainly analyze this data set and output a best possible estimate, T1, optimal estimate. And each one of these, you can do the same. So in other words, each one of us analyze the data set in the best possible way and send out output a transcript. Then the center simply takes an average of all those estimates. And you will see very quickly that naive approach is suboptimal. It's not optimal. Once you output the best possible estimate, no matter what you do afterwards, it cannot construct a best possible estimate. So in other words, learning collaboratively is different from learning individually. If you are the only person in the room, suppose you take an exam and try to solve one problem on your own, you try as hard as you can. But suppose we have a problem that we solve collectively. It turns out we shouldn't individually try our best way. And the constraint in this context is differential privacy. So what's the goal? The goal is to try to develop an optimality theory for federated learning. So we want to find the best possible estimates under this constraint. So that's A naught in the beginning. We want to evaluate the minimax risk under this constraint. And in particular, we want to know what's the difference between the one without constraint and the one with the constraint. And two, we want to construct an optimal estimate. And as I mentioned earlier, the naive approach is simply output the optimal, say, DP estimates from each server and then average. But it's suboptimal in many ways, because if that works, then it's easy. So what's new in this context? There are two things that's new compared to classical statistical estimation problems. The first is this privacy, statistical estimation under DP, differential privacy, on a single local machine. How do we solve the problem individually if we only have one data set? And two is distributed learning. Now we have many, many data sets. How can we do it collaboratively and optimally? So we are going to divide the problem into two steps. The first step is about differential private learning. So the first question is how to achieve privacy. Forget about optimality. I just want my output to be private. And the most naive approach is anonymize. Think about patient's record. Maybe the first column is patient's name, and certainly that's no good. So we remove that. Maybe the second column is patient's ID. Let's also remove that. Then starting from the third column on, it's all clinical records, blood pressure, height, age, or something like that. And naively, that's private. There's no name attached to the record. But that's not good enough. And the most famous example is a Netflix example. Back in 2006 and to 2009, for 3 years, Netflix ran a competition. It attracts the attention of many leading researchers in CS and in statistics, try to develop an algorithm to help the company sell their movies. So here, each row is a patient. If you watch a movie, if you like the movie, say very much, you give 5 stars. If you don't like it, you give 1 star. So each movie, after watching the movie, each customer rates the movie from 1 star to 5 stars. And no matter how many movies you have watched, you don't have enough time to watch all the movies. So the company wants to know, suppose you watch this movie that you haven't seen yet, whether you are going to like it or not. Because if they know you are going to like this movie, they will recommend this movie to you. Just like when you shop on Amazon or Taobao, they recommend products to you because they think you are going to buy the product. So the question is, how can we know that whether you like this movie or you don't like this movie? And the first computation was very successful. And the winning team was from AT&T Lab, and the prize was $1 million. And the company wants to do it again. But before they run the second computation, someone published a paper showing that the data set Netflix released for the computation, anonymized, together with some publicly available database, they're able to identify the customers. So that's not private. And of course, it's only about watching movies. Most people don't really care other people knowing what movies they have watched. But that's, of course, also depends on what movies you have watched. For some movies, you don't want other people know that you have watched the movie or you like certain types of movie. So that's the only computation. Netflix cannot run the computation again. So that's not good. Then the next question is, suppose we don't release individual level data. We only release summary statistics, whether that guarantees privacy. And the answer is no. And back in 2008, Homer et al., they published a very surprising paper showing that even if you only publish the mean, it doesn't guarantee privacy of the people who are part of the mean. And that's very surprising back then. Only after thinking about this more carefully, you realize that actually it's quite obvious why releasing mean is not private. And this is less obvious, so I'm going to give you an example. So why releasing X bar does not guarantee privacy. So this is a genetic data set about heart disease. The total of 136 patients. Let's divide into 3 groups. The in-study group are those with heart disease. And the out group are those without the disease, healthy people. And there's also a reference group. And suppose we only publish the mean. So each patient is a genetic data set. So each patient has 347,000 SNPs. So you can think of the matrix. Each row is a vector of about 347,000 dimensions. And we take the mean for those 50 patients in the study. So the mean itself is a vector of their length, very long vector. And the reference group is also a mean of the same length. Now we ask a very simple question. Suppose we have a new patient. We have a patient called Y. It's either from the study group or from the out group. Either the patient has a heart disease or don't have the heart disease. Based on Y and the 2 means, can we decide whether this patient belongs to which group? Because if we are able to do that, it means it's not private. We can identify the person whether this person has heart disease or don't have heart disease. And turns out you can. And you can do a very simple calculation. You simply calculate something called the Q value. It's the inner product of this y and the difference of those two means. And it's very surprising. You see that there's a clear separation between the two groups. If the patient is from the in-study group, the inner product is large. If it's from the out group, the inner product is small. And the question is why? If you think a little bit, you realize it's not that surprising. Because if y is one of the 50 people in the in-study group, then y itself is one term in that average. Is one term, because in the average it contains y itself. So in other words, if y is part of the study group, y is taking inner product with itself. That's one term, that's y. The rest has nothing to do with y. On the other hand, if y is from the out group, then y is not in this average, y is also not in that average. Y has no relationship with either one of those two means. And in high-dimensional probability, there's a well-known folklore saying that high-dimensional random vectors are almost always nearly orthogonal to each other. In other words, when y taking inner product with something else that has nothing to do with y, the inner product is very small. But on the other hand, if y is taking inner product with itself, remember y is a long, long vector. Sum of square of a long, long vector is very big. And that's why there's a clear separation between those two. And then the next question is, if this summary statistic doesn't guarantee privacy, how can we guarantee privacy? But before we do that, we need to define privacy. In abstract, we all know privacy very well, right? We all want privacy. But what's exactly privacy? It turns out there's no clear definition of privacy. And there are quite a few different notions of privacy. But the most popular one is what's called differential privacy. But in addition to differential privacy, there's also something called local privacy and other privacy. And differential privacy is a concept. It's very, in a way, it's very similar to robustness in statistics. It's a concept of protecting information of individuals when releasing statistical analysis results, and has been widely used by Google, Apple, Microsoft, and so on. Actually, one of my former students is now working for Amazon and developing private algorithms for Amazon. But most important application of differential privacy is by US Census. Because US Census only release summary statistics. And before, it didn't take privacy into consideration. But for the latest 2020 US Census, it's private. It guarantees differential privacy. And the definition of differential privacy is as follows. So roughly speaking, if you have a data set with, say, n patients, suppose you switch any one of the n patients with another patient outside of the data set. So you have this data set with n patients. You have another data set also with n patients, but the difference between the two is one patient. There's one patient that belongs to this data set, but not the other. So, and if we calculate a statistic called M, and basically it says if you only switch one patient, the value of this statistic doesn't change much. And it's very similar to robustness, right? In robustness, we also want properties of this type. But this is the mathematical definition of differential privacy. And there are two parameters. One is epsilon, and one is delta. And according to our earlier discussion, that anonymize the data doesn't guarantee privacy. and also sample mean summary statistic doesn't guarantee privacy. So the question is, how do we achieve privacy? And it turns out it's easy. If you only want to achieve privacy, you can achieve it through randomization. So earlier, I said releasing X bar doesn't guarantee privacy. If you add a random noise, coordinate by coordinate, it guarantees privacy. And here's the proof. For the Q value I mentioned earlier, taking inner product clearly separates the two data sets. But now after adding some noise, they're all mixed up. So clearly based on Q value, you cannot distinguish whether someone is in the set or not in the set. Not only that, this is just one example, Q value. Theoretically, you can prove after adding enough noise, there's no way, Q value or any other value, there's no way you can distinguish, you can determine whether one patient is in this data set or not in the data set. And here's one mechanism called the Gaussian mechanism. So for any statistics, say a d-dimensional statistic, if we define the L2 sensitivity, so two adjacent data sets, if this is bounded, then after adding this much noise, this is diagonal matrix, so it's independent Gaussian noise. After enough amount of noise, you can prove that this is private. There's no way you can distinguish. And this is so-called Gaussian mechanism. Another popular mechanism is called the Laplace mechanism. You don't add Gaussian noise, you add exponential noise. So we are going to use this notation, M subscript epsilon delta, to denote all statistics that satisfies epsilon delta privacy.
It doesn't matter what
In this case, it doesn't matter. As long as so this L2 sensitivity guarantees the level of the level of the noise. And certainly for specific problem and specific estimate, you can do a little bit better than this, say, general or naive recipe. But it doesn't you cannot gain substantially. There are results of that kind, and I will discuss a few in a moment. But we all know as statisticians, adding random noise is not good. It will downgrade statistical accuracy. And one famous example is image classification. The CFAR10 is a well-known test data set in image classification for machine learning algorithms. Even at the level of epsilon equal to 8, this is a very large number, so the privacy requirement is not very strong. Epsilon is often relatively small. See, at this level, the best known classifier is about 65% accurate, the classification accuracy. Without privacy, the best one can achieve 90%, so much more accurate. So in other words, there is a cost of privacy. When you ask for privacy, I can give it to you, but it's less accurate. But the question is whether the difference is about 25%, right? It's 25% less accurate. Whether that's a necessary price to pay for privacy or simply because we are not smart enough. There might be some other classifier. It guarantees privacy, and you will get, say, close to 90% of accuracy. So the general question is, given the epsilon delta dp constraint, suppose we really want privacy. now what's the best statistical accuracy that can be achieved? So in other words, in this example, whether that 65 is the best possible accuracy, or it can be improved to 85. So it can be divided into two parts. One is to quantify the cost of privacy in terms of statistical accuracy in a principled way, in a decision theoretical framework. Two is to develop efficient algorithm that can achieve the optimal performance under the privacy constraint. And in the last few years, I've been working with my collaborators. And Lin Jun was my former student now at Rutgers. And Yicheng is the one I just mentioned. He's now working for Amazon and developing private algorithms. Abhinav is my current PhD student, and Lassie is my postdoc. So we have studied several statistical problems under the privacy constraint. And we want to understand the so-called cost of privacy. And because of time constraints, I don't have time to go through all the details. Here's a list of the problems that we studied, from the simple Gaussian mean estimation to linear regression, high-dimensional linear regression, non-parametric regression, pairwise comparison, and federated learning for non-parametric regression, which I will discuss in detail in a moment. And the results can be summarized as follows. So in all these problems, if we don't care about privacy, they have been well studied. So the first column is the optimal, non-optimal performance without privacy, has been studied in the literature. So D is a dimension. So normal mean is a dimension of the mean. S is a sparsity. And alpha is a smoothness. For non-parametric regression, alpha is a smoothness. So in all these problems, we know without privacy, that's the optimal rate. And the second column is the performance of an estimate that guarantees privacy that we developed. You can see that it contains two terms. The first term is the statistical accuracy without privacy. So you have to pay at least this much. That's not surprising. What's more interesting is the second term. The second term is new. Because of privacy, we have to pay a higher price. And this higher price involves this epsilon. You can clearly see the dependence on epsilon. The smaller the epsilon, the higher the price you need to pay, because you ask for more privacy. So that's for a specific method. And here is the lower bound. Lower bound means that as long as you ask for privacy, there's no estimate that can do better than this performance. So whether this procedure is optimal or not, we can compare the two terms, the blue terms, because the black terms are the same as the first column. You can see that there is a logarithmic difference between the upper bound and the lower bound. The only matching terms are here. For pairwise comparison, we have the matching lower and the upper bound. It means that estimate we developed is optimal. And pairwise comparison is very special because it's non-Gaussian. Think about ranking of, say, tennis players. It's based on matches. So it's Bernoulli trial. And the random variable is bounded. And that's why we are able to get the matching upper and lower bound. But for all other problems, actually the difference is only logarithmic. And here we have log of 1 over delta and also log n. And we try very hard to try to eliminate the gap. I think we have a way to, now we have a way to close the gap, removing this log n term. But removing this log 1 over delta term is very difficult. Simply because we have no way to get a lower bound that depends on delta. The lower bound is obtained by studying what's called pure privacy algorithms. It's epsilon 0 privacy. But it depends on your attitude towards log. To some people, log is a constant.
This is all for adding Gaussian noise?
Yeah, the method we developed is all by adding noise, not always Gaussian noise. Here, we don't add Gaussian noise. But that, I think your question is very valid. That's why lower bound is very important. Because without lower bound, maybe adding noise is not the best way to achieve privacy. Maybe multiply by something is better, or doing something fancier is better. But with the lower bound, we understand that there's not much you can do. Not much can be gained by doing something other than other than adding noise. So from here, you can see that for most, if we ignore the log-term difference, we have obtained, we have constructed an optimal estimate for each of these problems. And also, by ignoring the log term, we can compare the first term with the second term. When the second term is negligible relative to the first term. Because if the second term is negligible, it means the cost of privacy is not dominant. It's negligible. But on the other hand, if epsilon is small enough, you can see that second term becomes dominant, which means that cost of privacy is significant. And that gives us at least some answer to the question of optimal differentially private estimates for that collection of problems. And the next problem we want to do is optimal federated learning. Now we have more than one data set. We have many. And the question is, how can we achieve privacy with, in the federated learning setting? So again, in the classical setting, we have one data set to analyze, and now we have many. And suppose we have servers or data sets in many, many different locations. How can we analyze the data such that, one, we guarantee privacy for each set, and two, we obtain the optimal, best possible estimate? So graphically, it's like this, and a version of this we have seen before. So given the data and a specific statistical problem, what's the optimal performance in the federated setting? So that's the question we want to answer. And the problem turns out to be quite interesting, but technically actually is also quite challenging. So so far we have solved a few problems, but for this talk I'm going to focus on a non-parametric regression. In non-parametric regression, we observe xi, yi pairs, and we want to estimate the regression function f. In high dimension, in linear regression, of course, this f is linear. And in some other parametric model, f has a given form. But in non-parametric regression, we don't specify this f. In the literature, in classical literature, related to non-parametric regression, people have also studied the so-called white noise model, where we observe a stochastic process. You can think of having this continuously, and also density estimation. And again, in the classical setting, people understand the relationship among those three models very well. Asymptotically, they're all equivalent. Turns out they're the same problem. Once you know how to solve one, you know how to solve others. And if you are taking any graduate level classes, I'm sure you've heard of these methods: kernel method, nearest neighbor, local polynomial spline, and so on. And you have also heard the theories, say minimax theory, adaptation theory, and so on. And one example is that if the function belongs to some smoothness class, we say hold the index alpha. Think of alpha as 1 or 2, differentiable or twice differentiable. We know the optimal rate. So in classical setting, we have very good understanding of these problems. And we also know global estimation, local estimation, we know confidence interval, we know asymptotic equivalence. So in other words, without privacy, under one data set model, the problem is solved. But now the problem is different. now we have m local servers. We have m data sets. And let's keep the problem simple, so make them homogeneous. So on the I server, we observe xi, xu, yu pairs. So each data set is of size n. On each machine, we have n observations, and a total of m servers, m data sets. And again, to keep the problem simple, we assume xu, the IID uniform, and the noise is IID normal 0, 1. And our goal is try to understand and distribute epsilon delta dp constraint. What's the best possible way to estimate f globally, and what's the optimal way to estimate this f at any given point? It turns out global estimation and pointwise estimation is different. That's also known in the literature. Unfortunately, the setup of the problem is a little bit complicated, and it depends on whether you have learned wavelets or not. If you have learned wavelets before, everything is straightforward. But if you have not learned the wavelets before, it's hard to explain. If you don't know wavelets, just think of as a more flexible version of Fourier series. So any function can be expanded in an orthonormal basis, like Fourier basis or wavelet basis. So a function can be turned into a sequence. Once you know the sequence, you know the function. So estimation of f is the same as estimation of the sequence, the coefficients. And the Besov class is a little bit complicated. It's defined in such a way. And it's similar to Lipschitz class or Sobolev class if you are more familiar with those classical smoothness class. So once we have the noisy observation, Zi is simply Xi, Yi pair. You have the noisy observations, you can compute the empirical wavelet coefficients. So you have the observations, you can turn into noisy coefficients. Once you have noisy coefficients, the problem almost becomes a Gaussian problem. And you can calculate the empirical wavelet coefficients. So in other words, you can turn a function into coefficients. You can turn noisy observations into noisy coefficients. And wavelets are organized according to what's called resolution levels. It has different resolution levels. And I don't know if you have experience when you go on internet. If the network is very slow and you try to see, say, a big picture, high resolution picture, sometimes you notice the picture comes to you first very rough, very fuzzy, then becomes clearer and clearer. That's encoded by wavelets. And sometimes you see the picture linearly. You first see people's hair, then forehead, then the face, then the body. So it goes from top to bottom. If that's the case, it's encoded by Fourier coefficients. And calculates the maximum estimated resolution level because we only have finite amount of data. So we can only estimate a finite dimensional vector. So we don't try to estimate the whole vector. We only estimate the first significant coefficients. And then on the I server, we use Gaussian mechanism. We add noise to the empirical coefficients. We get a transcript. So each server outputs a transcript that guarantees privacy. And here's more details in terms of what's the maximum resolution level and what's the amount of noise that you need to add. So because of time, I'm not going to explain this in detail. And then it can be shown that each server, the transcript from each server satisfy the epsilon delta dp constraint. And also the final estimate, the federated learning estimate is the average of those outputs. But what's very interesting, one is that we are able to obtain the optimal rate of convergence. The the minimax risk is given here. It has two terms. The first term is the minimax risk if you don't have any constraint, meaning that you are able to combine all the data without privacy, nothing. You can achieve this rate. But because of privacy, you have one second term. And this term is quite different from the first term. And a very interesting phenomena that if the second term is larger than the first term, then certainly the cost of privacy becomes significant. So if you ask for too much privacy, you can get it, but the estimate will be very low quality. And also from here, one interesting phenomena is that if we fix the total number of data, suppose the whole data set, the sample size, global sample size is fixed. Suppose you have two choices. One is you have many servers. Each server contains a small amount of data. Another is you have fewer servers, and each server contains a larger data set. It turns out it's strictly better to have more data and fewer servers. And that's very interesting. And so it's easier to retain privacy within a larger data set. 我不知道你们有没有看过这个武侠小说啊？以前金庸的那个小说里有句名言，叫“大隐隐于市”，就说你要藏在人多的地方，不要藏在那个高山深山老林里，很容易被人发现。That's exactly the same. Privacy is easier to achieve if you are in a larger crowd. And also another feature that's very important. The output from individual servers are not optimal for each local set. In other words, if you know you are going to work alone, you are not going to use this TI. But because you know you have many friends, you have other servers that work together, so your output and estimate that's suboptimal. But globally, it's optimal. Once you put all of them together, it's optimal. If each local machine outputs an optimal estimate, then the final estimate cannot be optimal. And there are some other interesting features that I don't have time to discuss. We also obtain the results for pointwise estimation, but let's skip that. It's different from the global estimation. And there are also some interesting features, especially the relationship between local estimation and global estimation. So let's skip that comparison with global estimation. The lower bound is difficult. And in classical statistics, we have a set of tools that enables us to study lower bound. And with privacy, actually, we don't have readily available tools to do that. So if you're interested in this type of research, it's a very interesting topic. How to develop general tools for privacy and for lower bounds. I'm going to skip that. And what I discussed here is the simplest setting. All the epsilon delta are the same. All the sample sizes are the same. And that can be generalized. You can have maybe different hospitals have different privacy constraints. So the parameters are different. But the results are very complicated. It's not a closed form expression. And there are many other statistical problems that can be studied under the federated learning setup, like hypothesis testing, confidence interval, multiple testing, and so on. So the field is wide open. And as I said, general lower bound techniques, and so on. And also non-IID setting, because in many applications, you cannot assume the distributions are the same. Another aspect of the problem is interactive communication protocols, not independent protocols. And this also is only one example of what's called multi-source learning. And the more and the more interesting problem, for example, transfer learning, distributionally robust learning, and so on. So the whole topic is very interesting, and it takes a lot more people. It will take a lot more people and a lot more efforts to study this type of problems. And I think I'm out of time, so thank you very much.
Great talk. Any questions?
Okay, I have a quick comment. So because we have been working on subsampling. Subsampling, essentially, you can think of you multiply this data matrix by 0, 1 matrix, then you subsample some rows, whatever. And we accidentally find, okay, if you generalize this 0, 1 matrix to some random projection matrix, in certain sense, we can also achieve this privacy. So you also briefly mentioned in your talk, okay, you are doing the additive with the Gaussian noise, but on the other way, if you multiply certain matrix, it could be achieve this privacy. But we didn't study the careful the minimax property. And also the second comment is recently we try to ask another question is that, but it's also in the context of subsampling, but could be potentially applied to this Yale's scenario is that in the finite situation, whether the subsampling or whatever multiplied by a certain matrix, okay, whether can beat the full sample estimator performance, something like that. Okay, could be also interesting.
Beating that is impossible because having full sample is the best possible way because even your procedure is only one of those procedures based on the full sample. Yeah, but achieving privacy, of course, can be done in many different ways. It will be very interesting to see whether that has good properties, both in terms of statistical performance and also in terms of privacy guarantees.
Any other questions?
Thank you, Professor Cai, for insightful presentation. I have two questions. The first question is about the data generating process in your presentation. That the conditional expectation of y given x is same for all data. So is it possible to generalize this framework to a setting that different regression function has different smoothness? And the second question is about privacy parts. And I was wondering if our target class is Holt class and some routine approach like local polynomial, can local polynomial approach, is there some approach for privacy protection for local polynomial? Thank you.
Yeah, second question first. I think if the parameter space is simpler, it's Lipschitz or Holder, I think local polynomial will be fine, or kernel method will be okay. But if the parameter space is more complicated, such as Besov space, I don't think local polynomial can easily do it. Maybe some fancier local polynomial can achieve that, but it will be very complicated. For the first question, because in this setup, there must be some common parameter of interest to all of them. So you cannot have smoothness, different smoothness for different servers. Otherwise, all the regression functions are different. But it can be extended to the setting that I think what you have in mind. For example, if we have an additive model. If we have an additive model, then we have many terms. Suppose, say the first term is the same, f of x1. The rest of the terms are different. But we are only interested in estimating the first term. I think that can be done.
Thank you.
Given the time limit, let's leave the other questions offline. Let's thank our speaker again. We will be back at 11.